everyone. In this video, we're going to look at evaluating limits algebraically. So that means you're given an equation instead of a graph. Okay, to evaluate limits algebraically, we always try direct substitution first. Because remember, we've seen some cases where the function value is equal to the limit. So sometimes to evaluate the limit, all you have to do is plug in. Here's an example. We have the limit as x approaches 2 of x squared minus 3x plus 4. So to evaluate the limit, we're just going to plug in 2 for x. We're going to get 2 squared minus 3 times 2 plus 4. And then we're just going to do order of operations. We'll get 4 minus 6 plus 4. Work it left to right. 4 minus 6 is -2. -2 plus 4 equals 2. So the limit equals 2. So we like it when that happens, because it makes our work pretty easy. But unfortunately, that is not always the case. So let's look at some other possibilities. If you try direct substitution and you get 0 divided by some other number, then that just means that the limit equals 0. Because 0 divided by some other number always equals 0. All right, here's an example. We have the limit as x approaches 1 of x minus 1 over x squared minus 4. So again, we're just going to plug in 1 for x. 1 minus 1 is 0. 1 squared is 1. 1 minus 4 is -3. So we get 0 divided by -3, which equals 0. That is the answer to the limit. So honestly, that example is not much different than the previous example. We really just had to use direct substitution to get our answer. Okay, well, let's say you try direct substitution, but this time you get a number divided by 0. Well, remember, we cannot divide by 0. So in this case, that means the limit does not exist. What's happening graphically is that there is a vertical asymptote in the graph of the function at that x value. Okay, here's an example. The limit as x approaches 2 of 1 divided by x minus 2. So if we try direct substitution, plugging in 2 for x, we're going to get 1 divided by 0, which we cannot do. So that leads you to the conclusion that the limit does not exist. And you're done. Okay, the third scenario, if I can get it to stop there we go, is you try direct substitution, but this time you get 0 divided by 0. Okay, now 0 over 0 is what we call an indeterminate form. So honestly, guys, this really leaves you with a question mark, okay? The limit may still exist when you get 0 over 0. So don't make the mistake of saying the limit does not exist in this case, because most of the time the limit actually does exist. You just have to do some algebra. Okay, so here are some things you can try to find the limit. The first one is factor and cancel. So in this first example, we have the limit as x approaches 4 of x squared minus 16 divided by x minus 4. So what we're going to do is we're going to factor the numerator. This is difference of squares. X squared minus 16 factors into x minus 4 times x plus 4, okay, divided by x minus 4. So notice x minus 4 over x minus 4 technically simplifies to equal 1, okay, but you can cross them out. So that leaves us with the limit as x approaches 4 of x plus 4. Well, now we can just use direct substitution. Plug in 4 for x, and we get 4 plus 4, which equals 8. So the limit equals 8. Okay, something I want you to notice in my work. Notice that I kept bringing the limit notation down until I use direct substitution. Okay, and you want to make sure that you do that when you're showing your work. All right, so you You've got to bring that limit notation down as you're simplifying that function until you use direct substitution. All right, as soon as you plug in for x, you can get rid of the limit notation. Okay, let's look at the next example. We have the limit as x approaches -2 of x squared plus 3x plus 2 over x plus 2. Now, one thing I do want to point out, guys, in both of these cases, if I tried direct substitution, I would get 0 over 0. Okay. I didn't show you that step, but that is the case. All right, so let's go ahead and factor the numerator. So in this case, we'd be looking for factors of +2 that add to 3. So that would be +1 and +2. And then notice x plus 2 over x plus 2 simplifies to equal 1. So we're left with the limit as x approaches -2 of x plus 1. And then we can just do direct substitution. And we get -1 as the answer to the limit. Okay, another thing you can try is to just simplify the function. So in this case, we have the limit as h approaches 0 of 4 plus h squared minus 16 all divided by h. Okay, now notice, if we try direct substitution, if I plug in 0 for h, I'm going to be left with 4 squared, which is 16. 16 minus 16 is 0. And then if I plug in 0 for h in the denominator, I still get 0. So we do get 0 over 0. Okay, so what we're going to do, we're going to start with this 4 plus h squared. Now remember, you guys, that means 4 plus h times 4 plus h. Don't make the mistake of saying 4 plus h squared equals 16 plus h squared. That is a common mistake where students just square both terms. That is not true, okay? The meaning of the exponent is the exponent tells you how many times to multiply the base times itself. So 4 plus h squared equals 4 plus h times 4 plus h. Okay, so that means we've got to multiply all that out. Or FOIL, sometimes we use FOIL, first, outer, inner, last. Okay, so 4 plus h times 4 plus h, if I multiply all that out, I'll start with 4 times 4, which is 16. It's basically a distributive property. 4 times h is 4h. H times 4 is 4h. And then h times h is h squared. I'm just bringing down the rest. Okay, let's go ahead and combine our like terms. So notice, first of all, the 16s cancel out. Positive 16 plus negative 16 equals 0. Okay, 4h plus 4h, that equals 8h plus h squared all over h. Okay, now what we're going to do next, we can still simplify this thing. I'm noticing we can factor an h out of the numerator, leaving 8 plus h. And now, the h over h simplifies to equal 1, so we can cross those out. And then that leaves us with the limit as h approaches 0 of 8 plus h. And now we can just do direct substitution, plugging in 0 for h. And so we get 8 as the answer to the limit. Okay. Here's another thing you can try. It's called multiply by the conjugate. You'll usually recognize when to do this because the function usually has a square root as part of that function. So that's when you want to multiply by the conjugate. But I do want to point out, if we plug in 7 initially, we are going to get 0 over 0. Okay. So then the next thing I would do because of that square root is I would multiply by the conjugate. Now, what the heck is the conjugate? Well, the conjugate relates to the expression with the square root. So square root of x plus 2 minus 3. The conjugate of that is the square root of x plus 2 plus 3. All you're doing is changing that sign in the middle to the opposite. Okay, now, to make sure we don't change anything, we're going to put the conjugate over itself. So technically, we're just multiplying by 1, okay, which isn't going to change anything. It's just going to put this in a different form. Okay, so then we're going to multiply straight across. I'm just going to put some parentheses around here. This circle. Distracting. Okay, so we multiply out the numerator. Here's where you will see why multiplying by the conjugate is helpful to get rid of that square root. Square root of x plus 2 times square root of x plus 2 is just x plus 2. Because if you multiply the square root by the square root, you technically get square root of x plus 2 squared. Square root and squaring, those are inverses, they undo each other, so that just equals x plus 2. Okay, now, square root of x plus 2 times 3, okay, we're just going to write that as plus 3 times square root of x plus 2. Now, you'll see what happens here in a minute. Okay, then negative 3 times square root of x plus 2, so that would be minus 3 times the square root of x plus 2. Okay, and then negative 3 times 3 is negative 9. Okay, now at first it looks more complicated, but look what happens to your middle terms. Your middle terms cancel. Okay. All right, now for the denominator, we are not going to multiply this thing out. I'm just going to put these in parentheses, to indicate that we are multiplying them together. Okay, now let's keep simplifying that numerator. So the middle, well, the radicals canceled, okay? Now we have 2 minus 9, and 2 minus 9 equals negative 7. So you're left with x minus 7 in the numerator, and that's over x minus 7 times the square root of x plus 2 plus 3. Okay, so now you'll see, and this is why we didn't multiply out the denominator. Your x minus 7 also simplified to equal 1. So this simplified now to 1 over the square root of x plus 2 plus 3. And I think we are now to the point where we can try direct substitution. So if we plug in 7 for x, we get, well, 7 plus 2 is 9, square root of 9 is 3, and then 3 plus 3 is 6. So this will all end up just equaling 6. And that would be the answer to the limit. So again, this is what we call multiply by the conjugate. I know it looks a little confusing at first, but once you start getting the hang of it, it's actually not too bad. Okay, you guys. The last thing we need to talk about are piecewise functions. Sometimes you're given a piecewise function. So anytime you're evaluating the limit of a piecewise function, you always want to evaluate the one-sided limits. So this would go back to the fact that the two-sided limit only exists if the one-sided limits are equal. Okay. So here's an example. We're given this piecewise function, and we're trying to find the limit as x approaches negative 2 of f of x. And this is a two-sided limit. So remember, that means you're approaching negative 2 from the left and from the right. So let's just go ahead and do that. Okay, so I'm going to start with the left-sided limit. Okay, now, think about your number line for a minute. Let's just say negative 2 is right here. If we're approaching negative 2 from the left, all those values are less than negative 2. So we are going to use direct substitution to evaluate the limit, but like which expression do we plug into? X minus 1 or x squared minus x plus 3? Well, in this case, we would plug into x minus 1 because that's when x is less than negative 2. So this would just equal negative 2 minus 1, which equals negative 3. Okay. Let's evaluate the limit as x approaches negative 2 from the right. So let's go back to our number line. If we're approaching -2 from the right, those are all values greater than -2. Well, when x is greater than -2, f of x equals x squared minus x plus 3, so that's what we're going to plug into. Okay, so this will equal 4 plus 4 plus 3, which will equal 11. Okay, I'm noticing something. We got different answers for our one-sided limits. So that means the two-sided limit, I'm not going to say equals, I'm going to say the two-sided limit does not exist. And the reason for that would be because the left-hand limit does not equal the right-hand limit. All right, let's look at one last example. Same idea, we're given a piecewise function, we're evaluating a two-sided limit. The limit is x approaching 2, so we're going to start with our one-sided limits. So if x is approaching 2 from the left, that's when x would be less than 2, so we're going to plug into the x squared. 2 squared is going to equal 4. Okay, let's evaluate the limit as x approaching 2 from the right. So if x is approaching 2 from the right, that's when x is greater than 2. And so in this case, we're going to plug into the 2x. Well, notice 2 times 2 is also 4. So in this case, because our one-sided limits are equal, we can say that the two-sided limit equals 4. All right, guys. So those are the main things that you have to think about when you're evaluating limits algebraically. But remember, we always try direct substitution first. So you always know how to start the problem. It just, what happens after you try direct substitution, then, from there you kind of know where to go. So, all right, we will definitely practice this some more in class. And as always, thank you for watching and have a good night.